So we're going back to a little bit of just review, basic theory of linear differential equations. Again, some new stuff and some old stuff just put together and how different topics in mathematics coincide with each other. So this is actually a nice way to go into linear algebra because we're going to talk about the Worskin in a little bit. But again, just going back to our basic higher order differential equation. And again, we're still solving for these type of things, but the most important thing we're going to be dealing with in this case is how are something called linear independent. We've talked about that in the past, but what does it really mean to be linear independent? And what's the main focus on those kind of situations? Now, the process is, in order to get an actual solution, we need linear independency. Okay, so again, this is a general theorem going over every single type, like, for n powers. So again, what that means is we've talked about just, y squared or y to the second power or primes or double primes. Maybe an example of y triple prime, but this is now going even higher. 4, 5, 6, so forth. Okay, so the general theorem is basically just the exact same process. Given any type of differential equation with any differentiable power, we can solve for it given its initial conditions. Now, again, since we're now talking about in theory the higher powers of it, and not just first or second powers, we have to talk something called the Worskin. Okay, so let f1 through fn be the polynomials of these portions. So in other words, these p1s, all the pn's, that's what these represent. The Worskin is basically the functions themselves, a matrix of a function themselves with its respective derivatives going straight down. Okay. Now, when we take the determinant of this, that's what's called the actual Worskin, not the actual matrix, but the actual determinant. So the determinant of this matrix is the actual Worskin itself. Okay. Again, we'll talk about that in a little bit more detail. Okay. Now, again, going back to homogeneous situation, if we have this situation here, again, now it's any power differentiable. The basic solution is always going to be like this. Same process, nothing has changed before. Again, now we just have to say this because now we're going into nth differential power. But this is roughly what we're going to be doing in this section, more importantly. Linear dependency and independency. Okay. Now, again, we've talked about how to certify what it means to be linear independent itself, or linear combination, but we get much more in detail in this section itself. Okay. So if we have linear independency, meaning that each can express as a linear combination of each other, meaning there exists some c's and c1s of f functions. If I just bring this over, it's now a linear combination of this one or any other ones itself. Okay. So that's what's called linear dependency. So I could pick one. So if I bring this all on the other side, now this first one is linear independent of the rest of them itself. Okay. Otherwise, it's called linear independency if I cannot do that. Okay. So it's an interesting topic and what it actually really means for it. But the next theorem is actually what is most important because it sums up everything we actually care about when it comes to solving for differential equations. So let f1, y1 all the way to fn be solutions and solutions of this differential equation on this interval. And let p1 all the way to pn be continuous on a and b. Then the following are equivalent, and this is the key thing. Okay. So this right here means we can actually find a solution to our differential equation. So if y1 and y2 are all linear independent, meaning, again, because they're all equivalent, the Worskin is a non-zero at some point, and also it's non-zero at all points within the interval a to b. Okay, so if you were asked to find linear independency or to show that two solutions are linear independent to each other or multiple are independent of each other, is basically stating this, or vice versa. If I say if you say given the Worskin is non-zero, therefore you know it's linear independent. On the flip side, to show that you cannot actually find a solution, is this one, linear dependency. Therefore, the Worskin is actually 0 on all points in A and B. Now, in most cases, it's easier to show one or the other. Some are more difficult than the others to show itself, but not too difficult once you get the hang of how to do each individual case itself. Okay. So, for example, we're going to do B first. Show that the functions are linearly independent or linearly dependent on each other. Okay. So, given our functions, so there's two different ways to show this. We could see, is there a combination of both of them that can give you the other one? Or we could just show that the Worskin is 0 or non-zero. Okay. So just for a little bit of practice, we'll talk about the Worskin for a minute. So I'll just call it W for short. So according to our definition, is just the functions go on top. So F1, F2, and F3. And we always want a square matrix. So what that means is, since we have three functions, we want a 3 by 3 matrix. So we take the derivative twice. So take the derivative once. And then one more time. And then we take the determinant of a 3 by 3. Remember how that goes about is you pretty much, this goes away and are broken down here. Okay. And within these matrices themselves, is this process. So if I get rid of this column, this goes here. And I do the same thing on the other side. So now this is the middle, get rid of that, so it becomes the rest of the other 4. And then lastly, the last column. And then from here, it's this is 2 by 2 matrix, so it's crisscross when you multiply. So multiply and then subtract the multiplication on the other side. Negative, negative makes a positive. This becomes 0. This becomes 0, so we get that. This all goes away, and distributing, which gives me 2. But again, this is not equal to 0, so they are independent. So that's how you show the Worskin is actually true or not. So now let's go to A. So A is a little bit more complicated. So I want to show you both ways you can actually do this, so you can see which way you feel more comfortable going about doing independency. So the first way is seeing, are they actually a linear combination or not? Okay. So in other words, given one of these solutions, is it a combination of the other two somehow? And if you notice, because F3 has a minus or plus, it may be actually, this one goes from here, and this one might go from there. So the only difference between this function and the rest is this one's multiplied by a 3, and this is multiplied by a 2. So really, F3, or the function, F3 function, can be represented as 3 times F1 minus 2 times F2. So it is a linear combination of the other two, so this is dependent. Again, the alternative, if you like to, just do the Worskin. Unfortunately, the Worskin this time is a little more difficult to do it because you have multiple things you have to, it doesn't simply break down nicely, like the last one here, because we have EDXs. So the derivative of e to the x is going to be the same no matter what. So this also applies just using a chain rule. This is all the same. And this goes from here. And then you do the same thing as here. Break it down and get the determinant, and you eventually get 0. So they do actually work out with each other. And like I said, sometimes one is far easier than the other one. So as you could tell, this is way easier than using the Warskin. But it's, whatever you feel more comfortable doing. Now the last part is, well, how does this work for non-homogeneous case? And that's the key thing. So for homogeneous case, that makes sense. But for non-homogeneous, it's a little different. Okay? Now, again, we're still trying to solve for differential equations, right? This is just going over how to show that the functions or some answers or solutions are linear independent or not. So let's go to the more difficult one, which you're going to be seeing more going forward. The non-homogeneous case. So for a non-homogeneous case, remember we always have a particular solution. And our particular solution for a non-homogeneous equation, looking like this, will always be the same situation as we've done before, right? So we'll break it down which method we're going to be using. And eventually, we have, again, our two parts. The particular solution and therefore our non-homogeneous solution. So this is the homogeneous solution, and this is the non-homogeneous solution. Same situation, something that we haven't done anything brand new about. However, because of this theorem and going forward, we can actually solve for things if we're given a lot more situation-wise. So, for example, this is a third order now. So we want to find a general solution to this, and it looks like a horrible mess going forward because there's a lot of stuff happening. But they give us a couple things. They told us a particular solution to x squared, a particular solution is equal to x squared for the same situation up to here. So if you notice, that's the first part. And there's another particular solution when this same thing is equal to negative 12 e to the negative 2x, which is about here as well. And then finally, we're told the homogeneous equations are these. So according to the principle of superposition, we can go from here to here by a constant, and that constant looks like it's going to be times 2. So the answer to this will be, well, our particular parts put together. So this first part is the same, so it's just going to be x squared plus, and because this is 2 times this part to get up to here, I'm just going to multiply this by 2. So this is the particular parts, and now we go to the homogeneous part. And we just plug those in individually with C1. And there we go. So when it comes to solving for these type of portions, again, we can use our rules. In this case, they gave us the whole portion, but eventually we will probably just end up doing each one individually and then put it all together.